Hello and welcome to another tutorial which is going to be very exciting, in which we are going to discuss a project called as YOLO object detection. So what we are going to do in this project is we are going to perform object detection in an image or a video. So given an image, finding the objects or detecting the objects or detecting and locating the objects in an image. So that's the objective of this project. So what is YOLO? So YOLO stands for you only look once, right? So what is this YOLO or you only look once? It is a family of deep learning models used for object detection in images and videos, right? So detecting objects in an image and locating those objects in the image. That is what YOLO is used for. Right. Now, how YOLO, in fact, YOLO is a neural network. It's a deep neural network. So, and it is trained, it is the YOLO model which we are going to use in this project. It is pre-trained, it is already trained on the dataset called as COCO, right? So, it is trained on the label dataset called as COCO. So, in the COCO dataset, the objects in the image are marked with the bounding boxes, right, and class labels, right. So these objects are marked with the bounding box. That means if there is an object, so a rectangle is put around that object, and it is and a label is given to that object. For example, if the object is car, so a bounding box or a rectangle is put around the car, and the label like car is given there. So once that's how this YOLO is trained. YOLO is trained on the COCO dataset, and this COCO dataset contains the images. And what are those images? Those images contains the objects, various objects like car, a person, right, or a cat or dog, or any other object. So there are near about 80 objects covered in COCO dataset, right? So there will be an image which will contain multiple objects. So that image will be there in the COCO dataset, and those objects in the image will be having the bounding boxes around those and labels with them. So there are numerous such images in the COCO dataset. So those images are used to train this YOLO model, right? So this YOLO which we are going to use here, that is pre-trained. That means it's already learned to detect the object. It is pre-trained. We are going to use it, ready-made pre-trained model we are going to use. So the bounding boxes, and the next important concept which we'll need here in this project is bounding boxes and class probabilities. So this YOLO algorithm will the output of the YOLO algorithm will be the bounding boxes around the detected objects, right? So we are going to give an unknown image. We are going to give a new image to this YOLO model, and we are going to ask detect the objects in this image. So what this YOLO will output? This YOLO will output the bounding boxes around the objects in the image, right? So this image may contain multiple objects, right? So this YOLO will put the bounding boxes or the rectangles around the objects and the labels, right? Now, what are the different layers in the YOLO architecture? So as I said, YOLO is the deep neural network, right? So therefore, it will have the layers which are common to the neural networks which are used for object detection tasks. So there will be layers like convolutional layers, batch normalization layers, then leaky ReLU activation. This YOLO uses this leaky ReLU activation function. Then there will be pooling layers. Then there will be fully connected layers, the skip connections, and then finally the output layers, right? So the there is not necessarily only one output layer in YOLO model. So there can be multiple output layers, right? There can be more than one output layers in the in the YOLO model, right? For example, YOLO, the version which we are going to use is called as YOLO 3, YOLO version 3. In YOLO version 3, there are three output layers, right? So what are the uses of those three output layers, right? Those three output layers and detects the objects at various scales. For example, small scale, medium scale, large scale, right? So that's why these output layers, there can be multiple output layers, each output layer detecting the objects of various different scales, right? So that's so the and these output layers will detect the class probabilities. Class probabilities means, if you know, as I said, the YOLO is trained on the COCO dataset, which has 80 objects, right? 80 different objects, right? So those objects are called as classes, right? And what is the, for example, let's say YOLO detected some object, and what is the probability of that object being a cat, right? Being a rat, being a person, being a car, etc. That is called as class probability. So here class is nothing but let's say person class, car class, cat class, dog class, right? So every object is called a class, and what is the probability of the detected object belonging to each one of those class, right? And definitely we'll pick the object with the highest probability. Then how many output layers are there in YOLO 3, right? So YOLO 3 features 3 output layers. So these output layers are designed to make detections at 3 different scales, right? So which allows the network to detect small, medium and large objects effectively. For example, let's say there are 100 layers in the YOLO model. So let's say last 3 layer are the output layers. For example, layer number 98, 99 and 100, these are the output layers, 98, 99 and 100. So 98 will layer number 98 will detect the large objects, layer number 99 will detect the medium objects, and layer number 100 will detect the small objects. That means the functionality of each layer is different, detecting the different of objects of different sizes or scales, right? Now now as we saw, the output layers or the output of the YOLO is the bounding boxes, right? And the probability of the class probability, right? That means it will output the probability of that object belonging to each class. So what is there in the bounding boxes? So each bounding box contains the x and y coordinates with width and height, objectness score, and the class probability. Now, what is this objectness score, or it is also called as confidence score, right? So this objectness score or confidence score is nothing but what is the how confident the model is that the detected object is indeed an object and is not part of the background or some noise, right? So, and these class probabilities are the probability of that object belonging to each class, right? Okay, so the confidence score or the objectness score I just now told. So this score represents how confident the model is that the detected object is indeed an object and not just a part of the background or noise. So this value is usually between 0 and 1, and a higher value indicates the higher confidence. That means the higher the value, model is more confident that the detected object is indeed an object and it's not a background or noise. And then these class probabilities are these are the probabilities of the detected object belonging to each of the classes that the model can identify, right? As we have seen, this YOLO is trained on COCO, which contains 80 different classes, right? So there will be 80 additional values, right? That means in the output produced by the output layer. So there, what are the values in the output produced by the output layer? The bounding boxes, then the confidence score, and the class probabilities. So these class probabilities are 80 values, right? Probability of first class, probability of the detected object belonging to second class, probability of the detected object belonging to third class, so on and so forth. So I have been talking about the COCO dataset, which is used to train YOLO, right? So YOLO version 3 is trained by using COCO. So this COCO, which stands for Common Objects in Context, It is a data set which is a large scale object detection, segmentation, and captioning data set, widely used for training and benchmarking object detection models like YOLO. So it is one of the most influential data sets in the field of computer vision and has played a significant role in advancing state-of-the-art object detection technologies. So these are the key aspects of the COCO dataset. It's a diverse object. It has diverse object categories. COCO covers 80 object categories, including a wide range of objects from everyday scenes, such as people, vehicles, animal, furniture, etc. So this diversity helps in training the models that are robust and versatile in the real world scenarios. Then it has large volume. The dataset contains hundreds of thousands of images. Each image is annotated with the detailed information, making it comprehensive resource for training and evaluating the complex models. Then rich annotations. Each image in the COCO has annotations for object detection and segmentation. For detection, the annotations include the bounding boxes around the objects and the class. So that means so there are thousands, hundreds of thousands of images in the COCO, and each image contains various objects, and those objects are annotated. There is a bounding box put around the object, and it is annotated. That means the label is put, right, and it is done for every object present in that particular image, and such image is given for training to YOLO, right. So thousands, hundreds of thousands of images are given for training the YOLO model. Okay, so why is it required to now let's before moving ahead, let's dive deep into the code. Let's discuss the code, and then okay, so I have already written the code just to save the time, right. So let me one more time tell you the objective of this project. So the objective of this project will be given an image like this. This is an image, right? You can see in this image there are various objects present, right? So like there is a person here, there is a bicycle here, there is a car here, car here, car here, car here, and so on and so forth. So there are many objects in this image. So what is our target or objective here? To detect these objects in this image, find the object. So there is an object here, right? So we are going to put the bounding box around this like this, and we are going to call it a person, right? Similarly, we are going to put a bounding box around this, and we are going to call it a car, right? So output of this project will be this image which you are seeing here, right? It's a plain image. There is no annotation here, right? So when we will see the final output, so the output will contain the bounding box here, person, bounding box here, car, and it will be done for every object present in this image. That's what the objective of this project is, right? So again, we are going to use YOLO. What is YOLO? It's a deep neural network. It is already trained. It is pre-trained on COCO dataset, right? So that means it has learned to identify the object. Now our task here is we are just going to input our image and ask this trained YOLO model to detect the images, detect the objects in that particular image. Okay, so this is the first part of the code. What we are doing in this part of the code, we are using some widget commands, right? We are going to use this widget commands, right? And what are these commands used for? So these are used to download the specific files from the internet. All right. So what are those files? So these are the 3 files we are going to download, right? So what is the first file, right? So the first file is downloaded from this website, right? And name of the file is YOLO version 3.weights, right? So what we are doing here, right? So this command here is downloading the pre-trained weights for the YOLO model, right? And what are these weights? So these are the parameters that the neural network model, that is YOLO 3 model, has learned during the training process, right? So, these weights are trained on the data set called as COCO, and we can detect 80 different object classes by using these trained weights. Right? So then we have second command, right? So this second command is used to download the configuration file, right? YOLO 3, YOLO version 3 dot configuration, right? So the configuration file contains various settings and the hyperparameters for the model, like the structure of the neural network. Structure of the neural network means what are the number of how many layers are there in the neural network, what are the types of those layers, right? For example, it's a convolutional layer, pooling layer, batch normalization layer, or the leaky ReLU activation layer, or the flatten layer, output layer, etc. Right? So this YOLO version 3.cfg configuration file contains all of that information. Right? Then we have the third file. See, these are the files which are downloading here. Right? This is the file. Right? This is another file. Right? And using these two files, right, we are going to prepare, or we are going to have our YOLO neural network or YOLO model, right? And the third file is the COCO.names file, right? So what is this COCO.names, right? So as we have seen that the YOLO is trained on the COCO dataset. So and this file contains the names of the classes that YOLO 3 can detect, right? So this COCO.names file, it's a simple text file with uh, one object class, right? One object class, one object class name per line, right? Per line, right? So there are this text file contains the uh, names of the classes, right? And one name is in one line, right? So for example, person, on one line you will have person, right? I'll show you, right? I'll show you the probably I have the presentation, I have this. Yeah, this is how the coco.names file look like, right? So we have person, bicycle, car, motorcycle, airplane, etc, etc. These are the classes, different classes, right? So there are 80 such classes. Okay, so we are going to download that also. Let me run this code. It's getting executed. Yes, we have downloaded all these three files, right? YOLO weights, YOLO configuration, and coco.names, right? We are going to use YOLO weights and YOLO configuration to make our neural network, right? So then next part of the code is we are importing some important libraries like CV, OpenCV, NumPy, and this CV2 underscore IM show, right? So what is this CV2, right? We are importing CV2. What is CV2? It's a OpenCV library, and we are giving it a name as CV2, right? So what is OpenCV? So this is a very powerful and widely used library for the computer vision tasks in Python. So this library provides the function for image processing, video capturing, object detection, and many other things, right? So then we are downloading, so we are importing NumPy, right, as NP. This NP is alias, or small name for this NumPy, right? So what we are doing here, we are importing the NumPy library. So what is NumPy used for? So NumPy is it's in fact a scientific computing package, right? So this NumPy provides the support for the multidimensional arrays and matrices, right? So and of course there are many other functions, mathematical functions, which are used to operate on these arrays, right? So here as we are operating on images, so and images will be stored as the multidimensional arrays, so we'll definitely need NumPy for processing those for processing, manipulating those images, right? So we'll need this. Then what is this CV2 underscore IM show? So this particular line is specific to Google Colab. I am using Google Colab here, as you can see here. So what we are doing here, we are having, see, had this been a Jupyter Notebook or some other Python environment, we would have used we would have imported the library called as cv2.imshow, right? cv2.imshow, right? So that is the standard function cv2.imshow in the normal Python environment. But as we are using Google Colab, so we are using the cv2 underscore imshow function, right? So which is specific to Google Colab, right? So in Google Colab, if you want to display the image, so this is used for displaying the image, right? If in Google Colab, if you want to display an image, you will have to use cv2 underscore imshow. So, but in the normal Python environment like Jupyter Notebook, you will use cv2.imshow, and of course the use of this is to display an image. Okay, let me run this. Yeah, it's working fine. Now this part of the code. So what this part of the code is doing? So here we are initializing. In fact, we are initializing the YOLO version 3 object detection model, right? By assigning by loading the weights and the configuration. See, what is after all a neural network consists of? It is nothing. The neural network is nothing but the layers, the stack of layers, right? Put one after the other. So this is the layers, and this is and if we have not trained it, we'll have to train this. But we want to use the weights. That means we want to use the pre-trained model. So we are mentioning this weights and the configuration, right? Configuration. So that means we are loading the model with pre-trained weights and the configuration, right? That is the layers in that, right? Okay, so then what we are doing, we are calling it as net, right? So this is the name of the our neural network, which is YOLO version 3, right? YOLO version 3, which is trained with these weights and having these layers, right? So what are the various components here? We have cv2.dnn.readNet. So this is a function from OpenCV, that loads the pre-trained deep neural network model, right? So this is the function. ReadNet is a function from the OpenCV, right? For loading the pre-trained model, right? So then we have the layers. Layer names is equal to name dot net dot get layer names, right? So net is nothing but this model which we have just now created. See, this is our model. This is our model, YOLO model, which we are going to use for performing the object detection tasks. This YOLO model is having these pre-trained weights and these layers, right? And now we are getting the layer names from this, right? So layer names of the layers we are getting, right? For example, the layer names like layer 1, layer 2, layer 3, so on and so forth, right? So these are not layer names actually, but just an example I'm doing. Maybe the layer names might be like the convolutional layer 1, convolutional layer 2, pooling layer 1, pooling layer 2, so on and so forth, right? Okay, so let me run this. So what we are doing here, we are just making our YOLO model, right? So we just now have the YOLO model, right? So this is YOLO network, YOLO neural network, which will be used for object detection tasks, right? So let me run this code. Okay, so now our model is ready, right? So in the next part of the code, what we are going to do, so here, so we are going to extract and process the information about the output layers of the YOLO model, right? So why we are going to extract the information about the output layers, because these layers, in fact, these are the layers which are performing the object detection task, right? So now we are just going to extract the information about the output layers, right? We are going to find what are the output layers, right? And why output layers are important? Because these are the layers which will be performing the object detection task, right? So okay, so here this first line, right? So layer underscore output underscore indices, what this line is doing, right? So here we are calling a method called as get unconnected out layers, right? So so this method we are calling on the YOLO model which you have created, our neural network, right? That is net. On this we are calling this, right? So so this get unconnected out layers method returns the indices of the output layers of the YOLO model, right? So what do you mean by indices? Indices means, for example, let's say there are 100 layers in this YOLO model, right? And let's say there are 3 output layers, which the names of the numbers of those layers are 98, 99, and 100. So 98, 99, and 100 are the indices of the output layer. So this method returns the indices of the YOLO model, output layers of the YOLO model, right? Okay. So so we are going to store the indices of the output layers in this variable layer output underscore indices, right? Okay. So now next part is we are going to check if the indices are wrapped in an extra dimension. That means if the output written by this is a 2D, right? For example, I just now said, right? So the output may look like this. So I said so 98, 99, 100, right? So this is one possible output which we can get from this, or it may be possible that it may be in one extra dimension like this, right? So if it is so, right, we have to flatten this. Flatten this means convert this output into 1D, right? 1D. So that's what we are checking now, right? So if layer underscore output underscore indices dot n dimension, whether the dimensions of this array are greater than 1, that means it's multi-dimensional, we have to just flatten it, we have to make it 1D. So we are going to call this flatten function, right? And this will flatten this, that means it will make it 1D, and we are again reassigning it to the same variable. Now the next line, right? So what we are going in the next line, so we are using the list comprehension here, right? So so list comprehension is basically a concise way to create lists in Python, right? So creating list in Python, we are going to create the list of the output layers, right? List of the output layers, right? So what is layer underscore names? Layer underscore names are the names of the layers, in the this net in our neural networks, the names of the layers in our neural network, right? So this layers underscore names hold the names of the layers, right? So we are going to iterate in this layer underscore output underscore indices. What is this layer underscore output underscore indices holds? This holds the output layers, indices of the output layers, right? Indices of the output layers we have here. Now we have two things here. The first thing is this list, and the second is layer names, right? So we are going to iterate through this output layers. So we'll get the indices of the output layers. For example, so as I showed here, we had 98, 99, 100. So I will take 98, right? So I will take 98, and the corresponding name from 98 will be retrieved from layer underscores names, right? So I'll repeat what I'm saying. So this layer underscore output underscore indices will, let's say, is looking like 98, 99, and 100. So this I will first take the value 98, right? And when I is 98, we are going in the list layer underscore name, and we are going to retrieve the corresponding name, right? Corresponding layer name. So that, for example, it may be layer 98. So for example, it will return layer 98. So that layer 98 we are going to put in the output layers, right? Then I will take another value called as 99. When I is 99, again we are going in this array or list, and we are going to retrieve the corresponding name of 99, right? So that means here, from here we got the indices, but we want the names of the layers, right? We want the names of the layers, right? So we are retrieving the names of the layers from the layer names, right? Corresponding names for the indices in here, and we are creating the list of the names of the output layers, right? And we are going to call it as output layers, right? So that's what this code is doing. Let me execute this code. Yes, we are done with this. Now let's move on to other part of the code, right? So here, so what is this code doing, right? So here we are just creating, we are just opening the COCO.names file. We are just opening the COCO.names file, which is a text file. We are going to open it in the read mode, right? And then we are using the short format, right? We are going to call that file as f, right? So coco.names are open in read mode. We are calling it as f, just a shorter name for this, right? And then what we are going to do, so this file is there, right? This file is text file is there, but in our program we are going to create a local variable which will be a list of the names of the objects which are there in coco.names, right? So coco.names, I showed you, it contains the names of the various objects, right? So with those names we are taking in the local variable called as classes, which will be a list, right? Again we are going to perform the list, we are going to use the list comprehension here. So we are going to read each line in this file, right? So by using f.read lines, right? And after reading each line, we are going to remove the trailing or following spaces, white spaces, right? By using this strip, right? And this will return us the name on each line, right? So each object name is stored on a separate line, right? So one execution of this for loop will return one name, and we are putting that name in the classes list. Then we are retrieving the second name, attaching or appending it to the classes list. Likewise, we will be doing it for all the 80 objects, right? So thus here we are getting the classes list, which will contain the list of the objects which YOLO can detect. Okay, let's run this. Yeah. Now finally, we are going to have our image, input our image, right? So for in which we want to detect the objects, right? So this is where we have, this is the name of our image, and in this Google Colab, where is this image, where I have stored this image? This image I have stored here, right? You see YOLO.jpg, right? You can see here, we have all those three files loaded, right? coco.names, YOLO version 3 configuration, YOLO version 3 weights, and this YOLO.jpg I have uploaded it in Google Colab from my local drive, right? Local drive from my machine I have uploaded it, right? So how to upload this YOLO.jpg? Just right click on content and click on upload, and you will get the path, just upload it. So you will have this file here. I have it here, right? YOLO.jpg. Why I did that? Just to avoid the complications of providing the correct exact path and all that. If I have that image here, I can just type the name of that image, and I'm carefree about the path of that image, right? So that image I am loading in the local variable called as image underscore path, right? So this is now the image, right? So in fact the path to that image, right? Path to this image, right? So I need not provide a path because my I have uploaded this image here in Google Colab. I just need to name the image, right? So now then I'm going to read the image, right? By using CV to OpenCV's IMRead function, I'm going to read the image, right? Which is there in this path, right? So I'm going to provide the path here. So this cv2.im read will read the image present here, and that image which is read, now I'm going to call it as img, right? Img is now our image on which we are going to work. We are going to detect object in that image, right? Okay, now we are just checking here uh, whether the image is properly uploaded or not. If the image is not uploaded, we are going to print this message, could not load the image, right? Else, that means if the image is uploaded properly, what we are going to do, we are going to we are going to resize the image for further processing, right? So cv2 underscore resize, right? The name of the image, that is img, is the name of the image here, which, right? So this img, right? Okay, then this we have this scaling factor, right? Scaling factors, how to by what amount you want to scale on x-axis and y-axis. So the scaling factors are 0.4 means 40%, right? So scale the image by 40% in the x and y direction, right? 40% of the original size, right? So that's what this fx, scaling factor in x, scaling factor in y, 40%, right? So that means the width and height of the image will be scaled to 40% of the original size in x and y respectively, right? Okay, so then what is this none, right? So this none in this particular context is the means that the output size is computed from the fx and fy scale factors, right? So this none means in this particular context the output size of this image is computed by using these scaling factors, right? Okay, so then we are going to call this shape on this image. So this img dot shape will return the height of the image, width of the image, and the color channels. Color channel means RGB, right? RGB channels. So that we are unpacking and storing this height, width, and channels in height, width, and channels local variables. Okay, let's run this. Okay, yes, now we have successfully uploaded the image. We have image with us now, and in that image we are going to detect the objects, right? So next part of the code, right? So this next part of the code is here. So what we are doing here, we are so here what we are doing, basically we are preparing the image into the format which is suitable for giving it as input to the neural network, right? So right, so what we are doing here, we are creating the blob, right? So what is this blob, right? So this, you see here, this blob equal to cv2.dnn.blob from image. So we are creating a blob, right? So this blob is nothing but a 4-dimensional array. This blob is nothing but a 4-dimensional array. We are creating a 4-dimensional array, also called as 4D tensor, and that 4D tensor can be given as input to the neural network. So we had this image, we have this image. From this image, we are creating a blob, right, which is a 4-dimensional tensor, and that 4-dimensional tensor will be given as input. 4-dimensional tensor or array will be given as input to the neural network, right? So this blob we are creating, right? So just the pre-processing on the image, right, which is required for the giving input for the YOLO model, right? Okay, so what are these various components, various parameters here? So this 0.00392, it's a scaling factor again. So this value is used for scaling the pixel values to the range that the neural network expects, right? So the pixel values are scaled between 0 to 1, and this is used. This is required for the faster convergence of the neural network during training. Now this second, again the next parameter here is the size of the output image, right? What is the size of the output image? It's 416 by 416. Why 416 by 416? Because the YOLO model is trained on this size of the images, right? YOLO model is trained on this size of the image. Then the next factor here is called as mean subtraction, right? That means subtracting some values. Will be subtracting these values from each pixel value. See, each pixel will have three values because it's a RGB, right? Each pixel will be RGB, red component, green component, and blue component, right? RGB, right? So here it is 0 0 0 means from each pixel we are subtracting 0 0 0, right? So that means we are not doing anything actually, but just it's a parameter required. Sometimes we set these values and we subtract these values from each pixel, right? So this is called as mean subtraction. Again, it's a pre-processing process step. So then this true here, this true indicates that the image should be converted to RGB format. The image should be converted to RGB format. That means, you know, the OpenCV load the image into BGR format, right? The image loaded by OpenCV will be in the BGR format. So we are converting it to RGB format because the neural network will expect the image in the RGB format, right? And then crop is equal to false means no further cropping or resizing should be done further, right? So we have this blob now. Everything, all this is called as blobbing process, right? So we have this blob of the image is converted into blob, and that blob is called as this blob. This is the name given to that converted image, right? And then we are giving this blob as input to the net, right? So net dot set input blob, right? And then we are computing the outs, right? So next line is outs is equal to net dot forward output layers, right? So this line actually performs the detection and returns the output, right? So this line is actually perform the detection and returning the output, right? So these output layers are the is the list of output layers which we obtained earlier, you know. So these are the layers, you know. In fact, these are the output layers, right, which we obtained, which we got here, right? So output layers, right? The output layers holds the names of the output layers, right? So and so these are the layers in the neural network which in fact detect the objects, right? And the result written by this will be stored net dot forward. Here we are performing the actual object detection, and the result is stored in the outs, right? Now what this outs will store, right? So as we have seen here, right, this is important to understand, right? What will be there in outs, right? So as we have seen here, the there are this is YOLO version 3, so there are three output layers. So the outs will hold, this outs will be an array which will have three values. Outs will have three values. That means output detected by the first output layer, then the second value will be output detected by the second output layer, and the third value will be output detected by the third output layer, right? So we'll discuss in detail in the next piece of the code, right? So I'll show you with an example. Just, yeah, you see this is detection is happening here, right? Yeah, we have detection is happening here. Okay, so now the detection has been done. Now the next step is to process the detection, right? Process the output, right? So we will need three arrays here. First is called as class IDs for all the classes. Then confidence, right? In this confidence, we are going to store the confidence score right, of the object, right? Confidence score we have discussed how confident the model is about the object, whether it's actually an object or some background noise, some background portion or some noise, right? And then the bounding boxes, right, for storing the bounding boxes for the objects, right? Confidence score, bounding boxes, and the class IDs of the objects identified. Class IDs of the objects identified, confidence scores of the objects identified, and the boxes, bounding boxes. In fact, the coordinates of the bounding boxes, right? So now let us process the output, right? So for out in outs, right? So let me first show you how out looks exactly, right? So yeah, the output outs might look like this, right? So if there are three layers, right? So the out will have three components. Outs will have three components. This is the first component, first value, right? So this first value is the list of the objects detected by layer 1, right? Then we will have second component, second component in this outs will be the list of the objects detected by second output layer, right? So on and so forth, right? So that's how your output. So I'll repeat what do you mean by that. So this is the list of the objects detected by layer, first output layer. So that's why it is called a detection 1, layer 1. Detection 2, second object detected by layer 1, right? And so on and so forth, right? So this is detection 1, layer 2. That means this first object detected by layer 2, second layer, second output layer, so on and so forth, right? So if in our case there will be three components here. This is this bracket. I hope you are able to see here. Let me show you, right? So this component, right? This is the first component of this outs, right? Which itself, this is an array, right? Containing the list of the objects detected by the first output layer. This is the second component or second value inside this outs. This itself is an array and contains the list of the objects detected by the second output layer, so on and so forth, right? Now, how does this detection look like, right? Let's talk about this. How does this detection looks like, right? So this detection is a vector, actually. It's a vector, right? So it which might look like this 0.5, 0.4, 0.2, 0.3. What are these values, right? So in this particular case, this 0.5 and 0.4 are the center coordinates of the bounding boxes, right? So we are written with this is returning as the center coordinate of the bounding, x coordinate and y coordinate, center point of the bounding box or the rectangle, right? So it's not returning the left corner, right corner, right? But center point of the bounding box, x coordinate of the center point, y coordinate of the bounding box, right? Center point of the bounding box, right? Then this 0.2 and 0.3, right? These are the width and height of the bounding boxes, right? Width and height of the bounding box. And this 0.9, right? This 0.9 is the confidence score. Again, confidence score means how confident the model is about this detected object, that it is indeed an object, not the noise or not some portion of the background, right? And the remaining values, right? So these remaining values here onwards, right? There will be 80 values here. There will be 80 values here, right? And what are those values? These are the class probability. That means 0.1 is the probability of this object belonging to class 1, right? 0.05 is the probability of this object belonging to class 2, so on and so forth, right? So this is what the outs will look like, right? I hope you understood. Okay, now we are going to process that outs, right? So we are going to iterate through outs, right? So we are going to iterate through outs. Now we are here, we are going to iterate, right? So for in the first iteration of the for loop, we will be having, we'll be having this, right? We'll be having this, right? So this out variable will take this value now, right? What value? This value, right? Out is now this, right? This out, right? This out, right? Okay, so and then after out takes this value, which is a list itself, list containing the detected objects, list containing the this is the first object detected, right? This is the second object, right? So on and so forth. Now we are going to process the first object, right? We are going to process the first objects, right? So out is containing this, and in the out we are going to iterate one, we are going to pick one object at a time and process that, right? So that's what we are doing here. That's what we are doing here, right? So this out is a list, and now we are iterating in that list, right? In that list, right? So what we are doing, right? So we are picking the first object, that is first detection, right, in the out, first detection in the out, right. So in this we are picking this now, right. So let me show you, we are picking this now, right. So this, right, and we are processing it, right. And what is this, how is it stored? It is stored like this, I have just now shown, right. It's stored like this, the center coordinates, the height, width, the confidence score, and the probability score, right. That's what this detection is, that's what this detection is, right. This is in this format, right. Now I am iterating, now I am processing this, right. Okay. So okay, so now for each detection, right, for each detection, what we are doing, we are finding the scores, the probability scores of the classes, right. And those scores are stored from fifth location onwards, from here 1 2 3 4 5, right. So so this is 0 1 2 3 4, right, and this is fifth location onwards, because list starts from 0 now. This will be 0 index, 1 index, 2 index, 3 4, right. And fifth location onwards, we have the probability scores, right, class probabilities, right. So we are going to retrieve that, that's why this 5 colon, right, from that means from fifth location onwards all the values will be retrieved, and those will be called as scores for that particular object, right. And then we are going to have the class ID is equal to np.argmax. So we are picking the maximum score, right. We are picking the maximum score, and we are calling it, we are having that class ID, because that is the maximum score, right. So and then confidence score is equal to scores of class ID, right, and the confidence is equal to the score of the class ID, right. So for example, the scores is array, no, this scores is array holding the class probability, scores is array holding the class probability. So we got its index, right. So we got its in fact what this class ID line, this line, in fact what it is doing. So this is finding the index of the highest score, right, index of the highest score, right, np.argmax, index of the highest scores in scores, right. In the scores array we are finding the index of the highest scores, right. So and that will definitely correspond to the class ID for the detected object, right. Then we have the confidence is equal to scores of class ID. So we are finding the confidence score for the most likely class, right, that is the class with the highest object, right. Now if the confidence is greater than 0.5, right, that means the object is detected. So we are checking the confidence score whether it is greater than 0.5 or not. That means we are just putting a threshold, right. So and if the confidence score is greater than 0.5, right, so this is the right, this is the object, this is indeed an object, so we will process it, right. So what we are going to do with that object, right, if the confidence score is greater than 0.5, what we are going to do, we are going to find the center, right. So center x is equal to int detection 0 into width and center y. So what we are doing here, we are calculating the center coordinates for the bounding box. We are calculating the center coordinate for the bounding box, right, center x and y coordinates. Then we are going to calculate the width and height by using w equal to int detection 2 into width, right, and this width and height are already, we have got those here, right. Width and height, yeah, here width and height. Okay, so we are computing the width and height, right, and then we have the rectangle coordinates, x is equal to int center x minus w by 2. So what we are doing here is basically we are calculating the top left corner coordinates of the bounding boxes, right. So because we have YOLO has provided us the center coordinates, not the top left. Once I know the top left corner coordinates, I can draw the with the help of the width and height, I can draw the rectangle, right. and then we are appending this to boxes array, right? Boxes array which we had here, right? Boxes array, this one. Okay, so we are appending the top left corner x and y coordinates and width and height. So with this information I can easily draw the rectangle. Then we are appending the confidence score and the class IDs, right? So that's what we are doing here, right? And that is done for every object, right? Every detection in each layer, right? If you run this loop, right? Okay, so that's done, we processed, right? And then we are going to perform something called as NMS boxes, right? So what we are doing here, basically, we have this NMS boxes, which is used for filtering purpose, right? So we are going to process only those filtered bounding boxes, right? So and let's go through the code one by one. So we have indexes is equal to cv2 dot dnn dot nms boxes, boxes comma confidence comma 0.5 comma 0.4. What this line is doing, this is applying the NMS, which stands for a non-maximum suppression, right? So this NMS filter for the overlapping boxes, just to neglect the overlapping boxes, right? We are neglecting the overlapping boxes, right? So where are the boxes? Boxes are here, right? So this 0.5 and 0.4 are the thresholds, right? So this is 0.5 is the threshold for deciding whether to keep the detection based on the confidence score, and this 0.4 is nothing but the NMS threshold for the overlapping boxes. That means if the boxes overlap more than this threshold, only the box with the highest confidence score will be kept, right? So this function will return the indices of the boxes which are kept, right? And we are storing those indices in indexes, right? Okay, so next we are iterating over the boxes, right? So for I in the range length of boxes, and what we are doing there, we are in the next line we are checking if I in indexes. That means this here we are checking if the current index I is in the list indexes, right? Is in this list indexes we have just created. That means whether it's there in the filtered or not, right? So what we are making sure here, that only the boxes which pass the NMS test or NMS filter will be processed further, right? Then x, y, wh is equal to boxes of I. In fact we are here unpacking the boxes boxes coordinates which are there in the boxes, and giving them to x, y, w and h, right? And then we are getting the label from the classes, right? See, classes is the list containing the labels, right? From that we are retrieving the labels, right? And for that we are doing this for each box, we are doing this for each box, right? Retrieving the coordinates, right? Retrieving the labels and putting the rectangle. We are putting a rectangle, right? This is putting the rectangle, right? So around this image, putting a rectangle in the image, right? So this where in the image we are putting the rectangle? In the x and y, at the x and y coordinate, right? Starting from this is the left corner, top left corner, and going down and going horizontally, vertically, right? Right? And this is the color which we are putting, right? So RGB, we are putting a green rectangle, and 2 for the thickness, right? And this is the label, we are putting the label, right? So these are the parameters. Image, in the image we are putting this label which we have just retrieved for this particular class ID, right? And the label is again just put near the top left corner, right? And this is the font, right? And the color and thickness of the label, right? Okay, so what is this 3 here? The 3 is the if it's in fact the font scale, right? Okay, so in fact what we did here, we are processing each of the boxes, drawing those boxes in the image, right? And labeling those images. right? Labeling those objects, in fact, right? So what is the result of this? The result of this is an image with the detected objects containing the bounding boxes, which are in green, and the labels again, which are in the green, right? Okay, so let's execute this. Yep, now we're done. Now let us finally let's see the image, right, by doing cv2 underscore IMShow. Yeah, this is the image which you got. You see the original image, if you remember, this was the image, right? This was the image, right? So we have put the, if you see, can side by side, if I can show you, you can see here, right? So we have, this is a person, right? Put a bounding box around the person, right? Then put a sorry, it went bicycle, right? So bicycle, you see bicycle, the car, right? It's a car, so on and so forth. So this is the final output which we got, and this is what we expected in an image. Detect the objects and locate those by putting the bounding boxes and the labels around it. So I hope you understood this project, you enjoyed this, and thank you so very much for watching this. Thank you very much.